Hey, this is Dr. J. I'm back with a little more from 8.3 today. A couple problems that just didn't get covered yesterday. We didn't talk about fifth roots. So I'm going to go ahead and do one of those. I think we did square roots and cube roots. I'll leave fourth roots to you as an exercise. I'm going to mention them. But we're going to start with fifth roots. So I want you to find all fifth roots. Of course, these are complex numbers. Of a complex number, how about 4 plus 3i? Okay, so quick review, a refresher. If you want to remember the formula, you're going to write z in the form r cis theta. Write the whole thing out, cosine I sine, or you can compress it into this abbreviated notation. And then your fifth root, 1 over n, so where n is 5. So n is going to be 5. So the 1 over n tells you the type of root. That'll be the nth root of r, cis. Now here's where you got to be careful. Theta plus 2k pi over n. I almost screwed that up last time. I think I managed to catch the mistake before it got us in too deep, but that was the idea. And then remember, k ranges starting with 0 all the way to 1 less than whatever n is. So in this case, we're going to stop at 4. Yeah, we'll stop when k is equal to 4. Okay, so that's just a quick review of the formula for finding complex roots. This is our z here. So let's go ahead and find r. That'll be the square root of 16 plus 9. So the square root of 25. Oh, I love it when that happens. So your radius or your modulus means the same thing, is 5. There is a notation you might like, just so that you have it in the future. The notation for modulus looks just like absolute value. It's the same as the value of r, but so remember, r is always positive. So we put these bars that look like absolute value bars to indicate that you must get a positive modulus. Even if the point is negative, or even if it has negative components, doesn't matter. You're squaring the square roots. You're adding the squares and square rooting it, so it's always going to come out positive. Don't ever put a plus or minus on your square root. You don't want to do that. Now you got to find the theta. So theta is tan inverse of b over a, so 3/4. Make sure you put that ratio in the right order. It's nice if this is in quadrant 1, so you can trust this if it's in quadrant 1. All right, so in this example, I picked a complex number in quadrant 1, which means that your calculator will give you the value. If not, if it's in one of the other quadrants, then you need to draw a unit circle or do some geometry in your head if you're really good at mental geometry. I like to draw the picture. That's what geometry is. And then you can figure out what the correct angle is. So theta is 0.64 radians. Always have this calculator set to radian mode. If you want degrees, just for your brain, it's about 37 degrees. But don't put that in the computer. It doesn't like degree measurement for your solutions. Solutions must be real numbers, and degrees are not real numbers. Yeah. Although they're very useful when I go to draw the picture, so I'm actually going to come back to that 37 degrees later. All right, so we've got our z. So our z will be 5 cis Use the radian measure, 0.64. It was actually 0.64350111, and I'm just going to say 0.64. Okay, so now we're going to do our roots. 1/5. It's a coincidence that the modulus is also 5. That's just a coincidence of the values that I have here. So it's 5 to the 1/5, no relation. CIS, we're using this formula. Theta is 0.64 plus 2k pi over 5. And now we're going to let k range from 0 to 4. That will give us 5 different roots. 5 roots. 5 fifth roots. The traditional symbol for a root is omega. It looks like a W. So omega 0 means what is my root if I plug in 0 into this recipe here. So it's going to be 5 to the 1/5, which is a decimal. We'll get to that in a second. CIS. You can just kill this when it becomes 0, so it's 0.64 divided by 5. When you plug in k equals 0, it's just going to kill that 2 pi term. It's just going to be gone. Okay, why don't I list them all out, and then I will simplify them all at once. So 5 to the 1/5, CIS. This time we're plugging in 1 for k. So 0.64 plus 2 pi over 5. So each time we plug in a different k, we get a different root. 5 to the 1/5, CIS, 0.64. Now we're plugging in 2 for k. So we're going to get 4 pi. Yeah, because 2 times 2 is 4. You could probably skip the plugging in and just notice the pattern. The first one, you have no plus pi's. Then you have 2 pi. Then you have 4 pi. You could probably guess the next one will be 6 pi plus 6 pi over 5. And my last one, I'll squeeze it down here, omega 4, 5 to the 1/5, CIS, 0.64 plus 8 pi over 5. These are your answers unsimplified. Simplify them a bit, but not too much. Just simplify them, give them as decimals. So 5 to the 1/5 power. That's the same as the 5th root. Is 1.38 approximately. All right, and then 0.64 divided by 5 is 0.128. So I've got 1.38 CIS 0.128. That's that one. They're all going to have this 1.38. So this is omega 1, omega 2, omega 3, omega 4. Now I'll get to the CIS in a minute. It's going to be cosine I sine. I just like to set it up like a factory and just run them all through. So now I'm just going to run through all of these. 0.64 plus 2 pi divided by 5. Well, that's neat. The angle, coincidentally, is the same as the modulus. It's kind of neat. Let's see. 0.64 plus 4 pi. I don't have a 4 pi button, so I'm just plus pi, plus pi, plus pi. I'm just adding it 4 times. If you come up with a more clever way of doing it, you certainly are entitled to do that. 2.64. I'm just rounding to 2 places. 0.64 plus 6 pi. And then divided by 5. 3.89. Although it's actually 3.90 if I'm rounding appropriately. And one more, this one down here at the bottom here, 8 pi. So I've got 0.64 plus 8 pi. 4, 5, 6, 7, 8. I know that's not the most elegant way to do it, but, and then divided by 5. All of these answers, a clue is they should all be less than 6.28, which is 2 pi. So if you get any angles that are beyond 2 pi, it means you've gone around the circle too far and you need to back up a little bit. It's also a mental clue. If you look at these and you see, you know, like I always do, write a decimal in the wrong place or something like that. This is your, you know, warning sign. If you write a decimal incorrectly and it ends up being larger than 6.28, you might have either written it down incorrectly or you just need to go back and rethink the value. All right, these are the polar CIS forms. This is really a compressed way of writing the answer. The other way to do it is with the E. It means the same thing. I'll get to that in a second. But this is not going to be how you're going to type it in. All right. This is just the polar compressed form, the CIS forms. We have to actually do cosine, I, sine to get the complex values. So now use cosine and sine to get, and R also, don't forget the R, to get A plus BI form. It's all done on your calculator. So do the modulus, multiply the modulus last. Just go cosine I sine of this guy. So we got 0.128. I mean, one thing you can do when you're doing this on your own is just do the cosine and the sine when you're doing this, and you don't have to then create a whole nother category over here. Now, I'm trying to demonstrate the two different forms of the answer, which is really what this section's all about. So I have a motivation there. So cosine first. So cosine of 0.128, and then multiply that by 1.38. So you're going to get 1.36. And now you're going to do sine. That's what the S stands for. 0.128 sine, multiply by 1.38, and then give it an I. So that'll be 0.18I. That's the CIS. Okay. And then you run through all of them, and they will all be standard complex A plus BI form. 1.38 cosine, and then multiply by, coincidentally, 1.38 again. So that's your A component. And then now do sine. Some of you might have a more expensive calculator than me. If you do, if you got one of these fancy TI 90 something or one of the, you know, Inspire calculators or something, there might actually be a CIS button. Hunt around for it. You know, you type this in, hit the CIS button, and bam, you get your answer pops out in front of you. It's almost too easy at that point. So now I'm doing sine of 1.38, and then times 1.38 again, and then give it an I, 1.35 I. And just keep going down the list. 2.64 cosine, I know, it's like watching paint dry, times 1.38. We finally got into the negatives. All right, good. And then the sine, 2.64 sine times 1.38. And then give it an I, so 0.66 I. Where am I at? 3.9? 3.9 cosine times 1.38. So negative 1.00. It's basically negative 1. 3.9 sine times 1.38. Oh, that one turns negative. So now we're in quadrant 4. Oh, sorry, quadrant 3. We're getting quadrant 4, I think, on the last one. 5.15 cosine times 1.38. Yep, we're back in quadrant, or we finally made it to quadrant 4. And finally, sine, 5.15 sine, and then times 1.38, and that gives us negative 1.25 I. So you have your polar form and you have your rectangular form. Okay. I can't let this go without showing you what's the relationship between these roots. It's a very geometric relationship. And that's where I like to look at the theta was approximately 37 degrees. Because when you're doing geometry, you have to think, geometrically using degrees and such. I prefer to think that way because I'm not sure when you see 1 point, something, does that look like an angle? But when you see 37 degrees, you clearly see an angle. So what does that 37 degrees mean? It means that your initial solution was approximately 37 degrees above the polar axis, or what we used to call the x-axis. All right. And then the modulus was 1.38. That's the length of the hypotenuse, if you think of that as being a triangle in trigonometry. So that's your R, 1.3. Okay. So that's what omega 0 means. And then now you have 5 roots, in a circle of 360 degrees. So you divide 360 by 5, and you get 72 degrees between each root. So 72 degrees would put me just about here. And that would be my next root, would be 72 degrees away from the last one. So just rotate 72 degrees. I went a little bit too far. So just put you right, just a smidge more than 90, right about there. Okay. So I'm not going to write it out again. This is it. This is omega 1. Okay. I'll show you a few more, though. I'll see if I can go all the way around. Now we're going to do another 72 degrees. That's going to put you, interesting. Why is omega 1 not in quadrant 1? Look at the value here. It makes me wonder if I made a mistake. So quadrant 1. Correction. It's 37 degrees divided by 5. Oops. Before I start drawing the picture, 37 divided by 5 is 7.4 degrees. Let's fix my picture a little bit. I'm glad we have this form. This is really my safety net here. I would have just kept talking and never even realized it was incorrect. So we're really at 7.4 degrees. .4 degrees, so much smaller angle here. All right, and then so my 1.38 is the length, and then that's my initial. So now it makes a little more sense. When I go to my omega 1, it's going to be, should be is the same length, and it should be 72 degrees of separation between them. So now these two first roots are in quadrant 1. And then go another 72 degrees. Now we're in quadrant 2. .72 more degrees. Again, I'm not using a measuring tool or anything. All of these should have the same radius. This is a big circle. And it should seem reasonable. Yeah, I could have probably gone a little bit further. They do make tools for this so that you don't have to approximate, but there we go. Now it almost seems too big, but that's okay. Let's just go for 2 more and finish this. So we have, this is in quadrant 3 now, so we're going to go 72 more degrees down to quadrant 3. And that'll be our omega 3. And then we're going to go 72 more degrees into quadrant 4. And that will be your omega 4. So geometrically, if you wanted to check your answer, I'm really glad I did, because had I not drawn the picture, I might not have even caught the fact that that was only 7.4 degrees. What was the 37 degrees? I should mention that. So these are the roots. Yeah. Your original point was here. I don't want to go too much further. I'll go off the screen. This was your 4 plus 3i. That was your original z value that we started with. That's the one that was 37 degrees. So the 37 degrees did affect the value, but I had to divide it by 5 to get the 7.4 degrees that the initial root lies above the polar axis. Okay. Also, the modulus of the original point was actually longer than it is in the picture. It should have been 5, but I don't have, my board's not big enough to go all the way to 5. And then its root is smaller than 5, so it has a smaller modulus. Its root is 1.38. At least the modulus is 1.38. Okay, so those are your fifth roots. I'll leave it to you. You've seen square roots, cube roots, and fifth roots. I think you can just repeat this process with a 4 for a fourth root or a 6 for a sixth root. It's the same basic idea, just a different number of spokes on the wheel. And I want to show you one last thing. This is sometimes referred to as the most beautiful equation in math. Of course, that's certainly a subjective term, but it's very, very common to call it that. If you Googled the most beautiful equation in math, I guarantee you would get this equation. It goes back to the polar form REI theta, where r is equal to 1. So we have EI theta. Now we got to make an equation out of this. Okay. So we'll just make a very simple equation. EI theta plus 1 is equal to 0. So it uses E, the exponential, natural exponential. It uses I, the imaginary. It uses the classic symbols from basic arithmetic, 1 and 0. And I want to find what is theta. So solve this equation for theta. So we'll move for the other side. Remember what EI theta actually means. It means CIS theta, cosine I sine. Now, to actually solve this complex equation, it's actually much simpler than it looks, all right? The right side is technically plus 0i, yeah? If you have a pure real number, -1 is pure real, then that means you have an invisible 0i. And so when you solve complex equations, you set the real parts equal to each other. Come over here. Cosine theta equals -1. And you set the imaginary parts equal to each other. Ignoring the imaginary, or you could actually write it, I sine theta equals 0i. You would just immediately divide both sides by I to get rid of it. So think about your unit circle. What angle has a sine of 0 and a cosine of -1? And it should be a standard angle on the unit circle. Cosine is -1. Sine is 0. And so this angle you all know as pi, or 180 degrees. And so that is sometimes called the most beautiful equation in all of mathematics, because when you put in your solution of pi, you get one equation that contains the 5 most important symbols in all of mathematics: E, I, pi, 1, and 0. And they all live together in one beautiful equation. Okay, so I hope you all enjoyed our time in complex polar land. My next video will be the end of chapter 8. It'll be the parametric equations. So I'd say we're about 95% the way done. This last lecture is not going to be too complicated. I just want to finish off the chapter this week. Okay? So Dr. Jordan signing out. Take care.